Well, it's time. Welcome back, everyone. We're just about to finish off midterm week, so it's about over the halfway mark, I was about to say. So welcome back. Today's class, we're not doing anything too major other than we're going to be starting off with the review questions led by the class. So I guess that's the biggest announcement, that exam 2 is going to be next Monday. Like we promised, it's only going to be over these sections and chapters specifically. With the odd one out, section 5.3, think of that one as really, it was kind of a preview to section 5.4. So that's the one section I'm not going to ask a direct question out of. It's really going to be more that you can expect. That was a kind of a cool sound. Not sure what that was. And so pretty much the difference is in section 5.4, what you're using is on the calculator, second bars, and either normal CDF or inverse norm. Aside from that, the other announcements are quiz 6 is due today, and I'll try to get those graded and returned as soon as possible. Quiz 6 is pivotal since that one is relative to chapter 6. So if you can do the problems on quiz 6, then that's a great way to study. Probably the better way to study, in my opinion, because that's something you're doing for credit. It feels higher stakes, which means you just memorize that stuff better when you're doing those kinds of things. Aside from that, quiz number 7 is going to be based on chapter 10. So if you decided to kind of just leave quiz number 7 on the back burner until after exam 2 is done, that would make sense. Sometimes you do need to be strategic. So if you decide to focus on the second exam, that's okay. Well, I think that's the total extent of the announcements, except let's just go through our standard reminders. Don't forget to print out a page of notes or write out your page of notes, however you decide to do it. And a pretty good reminder for that each and every time is try to get that done as soon as possible. If you're doing it on Sunday, that's not too bad. If you're doing it Monday morning, not horrible either. It's going to be more fresh in your mind. But you really want to do it as fast as possible so that if that's done as your very first step for studying, use your notes when you go to do these review questions. And you're deciding if the things on your notes even make sense. You're going to be able to decide if stuff is missing, where everything is even located in the first place. So I would make that your very first thing you want to do to study for the exam. Compile your notes, then begin studying the problems, and you might decide that you can fine-tune your notes a little bit here and there. Other standard reminder on the exam is don't forget your TI-84 calculator or your equivalent calculator model. Understanding how to use a calculator is part of the exam. So a great thing to add to your notes for every exam is just a quick instruction set on how to do basic things like calculating correlation coefficient, doing inverse norm, anything along those lines is super helpful. I'll bring spare calculators to class, but it's always good to have the one you're most familiar with and ready to go with. Well, I think that's it, folks. That's our full set of announcements. Any questions or comments about anything before we get started? Okay, let me pull up the participants window. Well, this is the exciting part of class. A student-led review is sometimes kind of tricky the very first time we do it, but we get better and better at it. So this is the point where we turn it all over to you. There could be kind of a student-led person who's choosing the questions, or it could be multiple questions. I'll just use the annotate to list them here. So all up to you at this point. Yeah, go ahead.
I was doing the sample exam last night.
Yeah.
And I noticed I was having problems in like chapter 3 and chapter 5 where we were, well, chapter 3 was the relationships and doing like the charts.
Mm-hmm.
Wondering if we could go over that again.
Yeah, so chapter 3, mainly the charts is what we're focusing on.
Yeah, just I kept getting the rows and the columns and stuff with my answers.
Gotcha. So not a specific part, more just the overall question. I think this is a great one to run through. So let's give this a try. We're going to use the method of screenshots. I forgot to actually bring the Word version of this with me. This file I have right here is called Exam 2 Class Review Questions. And when we're done with it, I'm going to place it right here so that's available. So here's our first question of the day. I'll bring in the parts as we get to the next parts. They say, how is the hatching of water python eggs influenced by the temperature of the snake's nest? That's kind of an interesting question. You'd think that it's got to be a certain amount of warmth for optimal. researchers assigned newly laid eggs to one of three temperatures: hot, neutral, cold. Kind of feel bad for those ones, so some of the eggs probably are struggling. The hot condition duplicates the warmth provided by the mother python, so it looks like hot is ideal. Neutral and cold conditions mimic the mother's absence, so that doesn't sound great. And here's the data on the number of eggs that hatched. So we have one variable going this way, cold, neutral, hot. One variable going this way, hatched, did not hatch. And part A is just about describing those variables. So let's go with that right up to start out. We decided to color code this. Let's see, maybe that wouldn't make sense. Let's just be careful with what we've got here. We just want an overall name for over here. It could be something like hatch. We have to describe the variable. Describing the variable hatches mostly deciding is it categorical or quantitative. But this is absolutely a categorical variable. Even if we're looking at numerical data, we're just counting the number of individuals, the eggs, that belong to each one of these conditions or categories. So hatch is categorical with outcomes hatched, did not hatch. That's kind of sad, but moving on to the next one, going this way, that's our second variable. This one, I guess the most thing that makes the most sense is just calling it temperature. So let's just say temp or temperature. It's also categorical with outcomes cold, neutral, hot. So we did, folks. That's our describing the variables. Any questions about that so far? Okay, usually a question like this one is not too big of a worry, because if you're doing this kind of question with a two-way table, it always is two categorical variables. So that's a big hint on this kind of problem. So next part. We want to know what percent of the eggs did not hatch. And when we go to calculate this, one of the thoughts that you might have is this should feel a lot like chapter 12. We could just change the wording to what is the probability an egg did not hatch? And we're asking the same exact question. So it's kind of neat in a way. So let's start off this by saying, what percentages of eggs did not hatch? We have to fill out the numerator and denominator. Anyone spot what the denominator should be on this one? Exactly. Just like in probability, that's the number of outcomes or the size of the sample space. So that goes down below. Next, we need to find the part of the problem that matches with this, did not hatch. That's just one of the outcomes of the categorical variable. Takes us this way. We have all these values here, but you want to grab the total of just the 58. So that fills out the numerator. The last thing to do, we're rounding to one decimal place. So this turns into 58. Oh, that's a weird spot. There we go. 58 divide by 187. It wants a percentage, so I'll just by default go times 100. And this will be 30.0%. Oh, 31. Thanks for spotting that. 31.0%. I think I said it wrong, and then I wrote it wrong, and then I looked wrong. So I finally knew something was off. Any questions, folks, with that first one? Okay, so these questions aren't too bad to start out, but they do get tricky. So we have to be pretty careful as we go forward. Gotcha. Let's take this table down with us as we go. So here's the next one. Part C. What percent of the eggs did not hatch and were in a cold environment? Just missed whatever that was. So for this one, the big thing that makes this a little bit tricky is that word there, and. It means two conditions happen simultaneously. We have did not hatch, cold environment. So when we go to write out the answer on this one, sorry, having trouble with my mouse here. There we go. When we go to write out the answer on this one, anyone spot what the numerator should be for this? Exactly. It's the intersection of the two conditions, did not hatch and cold. And that's only because we said and. I'll put a little box here to just kind of give some pseudo color coding to show where that came from. And when it says what percent of the eggs, we're talking about all 187 Python eggs. So that's our denominator. Any questions, folks, with that one? Oh, sorry, I missed some chats here. Comes out as 5.9%. Thanks, Ashlyn.
Why is it all of them?
Why is it all 187?
Yeah.
It came from this part of the wording. If it says what percent of the eggs, it means we're referring to all 187 eggs in total.
What percent of the whole eggs you would say? Oh, that's right.
Exactly, yeah. Those are conditional types of statements where. Sorry, say again?
If it was percent of cold eggs, the 11 that's the total number. Or 40% of eggs that didn't hatch it because you. If it was 4% of the eggs did not hatch and were cold would be the 58.
11 divided by 58, yeah. That might be our next question. Let's double check. Who knows? Part D, among the eggs that were in a hot environment, no, not quite, but kind of close, what percent hatched? So let's take a look at that one next.
I really appreciate all the times you've reiterated the context, because now I'm like pointing out the different languages.
Oh, gotcha. That's awesome.
The questions can be tricky if you don't pick the words.
It is. That's the worst thing about statistics is it's easy to crank out the numbers, but when it's so context heavy, the numbers become meaningless without paying attention to it. So this one is trickier now. It says, among the eggs that were in a hot environment. So from that statement right here, anyone see what the denominator ought to be?
Would that be 104? The denominator be 104?
Exactly. We're looking at this. Oh, didn't mean to scribble on it. There we go. So we're talking about just those eggs now. In a certain sense, it's almost as if we restricted our attention to just that. The hot environment is all that matters. So it becomes our denominator, 104. They are asking next, what percent actually hatched? Let's take a look. Yeah, absolutely. Reason we're grabbing the 75 is because we're only talking about the eggs in the hot environment and no other eggs. Actually, I think this is a good table to leave here. This is a tricky enough question. Let's kind of fix our color coding like this. When it says among the eggs that were in a hot environment, we're taking that value. And it also means none of those values matter at all. They're just eliminated from the table. We only care about this now. Later on, we'll call that conditional probability. We're only concerned about the condition of hot environment. Then it goes on to say what percent hatched. Oh, that's not going to work. Let's go this way. And as you said, it's going to be just the 75. We have to select now. So 75 goes up above. That means we're pretty much done with this one. Awesome, 78.0%. Look all right so far with these questions. Awesome. So again, these are some pretty tricky kinds of questions because it's all about orienting ourselves on the right part of the table. But with more practice, it's not so bad. I'll leave the color coding and the highlighting on the table here just to convey how we got that answer. And here's our next one, part E. Among the eggs that hatched, what percent were in a cold environment? So kind of similar to the last question, but this time when it says among the eggs that hatched, we're looking at that first row right here. These are the hatched eggs. Oh, 72.1.
I put the other one on my paper and probably let me know.
Actually, let's leave it here just for 1 second. Let's suppose this was a real exam question and you left your answer just like that. I would go something like this when I go to grade it. I usually like to use green for growth is a thought. I'd go like this. Then I'd say, you've got the answer. You just made a mistake in the calculator. If we did need that number in a different way, you might have lost something like a half a point out of a 4-point problem. Nothing too major. But if it looked like this is the problematic one, because at this stage, I didn't mean to grab the red pen. I'd never grade in red. But if it looks like this, then we could lose serious points on this. It could be something like -2 or -3, because now there's no basis for partial credit since we have no idea how we got the number. So always try to write out stuff that goes like that on the exam anytime you're about to use a calculator. And again, if for a part D, if all we're doing is just getting a number and nothing further happens, even if you got that wrong, you would get full credit for just getting that there. I would just assume it was a simple calculator mistake. That I've forgotten the actual answer. Anyone recall what it was? Awesome, thank you. So we're moving down the list. And now part E says, among the eggs that hatched, what percent were in the cold environment? Let's use that little strategy of just Xing out part of the table that doesn't matter. When it says among the eggs that hatched, that means all of this is gone. So we can just eliminate it from our view. Our denominator is going to be the 129 eggs. Anyone see what the numerator should be? Exactly. We want to know what percent were in the cold environment, but only among the hatched eggs. So this will be 16 divided by 129. Awesome, thanks, Jalissa. Next, all we do is throw it into the calculator and we're on our way with that one. So let me see how this comes out. 16, 129 times 100. And yeah, 12.4% on this one. So that's about how the question's going to go on the real exam. When we did this as a problem in chapter 3, we also had other questions like marginal distributions, conditional distributions, and some graphics. But I'm also going to focus on the problems that we just did here on this one example. This is going to be the more direct kind of question I'll ask. Well, any last questions on this problem here or other problems that we should go to?
I wanted to talk about when we was 5.2.
Yeah.
We talked about mu and sigma and then putting it on that giant graph with the 34% and then 13.5, 2.35.
Yeah.
I wanted to know if we could talk about when the mu is the median or the mean, and then when the sigmas are the IQRs or the, or no, not that, not IQRs. Whatever defines sigma. Just some refreshes on that.
Gotcha.
When we're doing the, like when we're scaling those and making our own graphs,
Yeah.
we change the standard deviations by six. That's what it is, standard deviations. But I wanted to discuss what that was again, whether it was median or mean or.
Gotcha.
Yeah.
Let me know if I'm on the right track with this question. So you're mostly asking what would the sigma value and mu value indicate? Is that what the major question is?
Pretty much, yeah. When sigma is the median, what is, or no, when the mu is the median, what is the sigma?
So I'm not too sure about that question. How'd you say the first part? When?
Where do you go?
I don't know. That, to be honest, that whole section.
So we talked about when, remember when we did like the IQRs, and then if it's IQR, you use this value?
It sounds like you're talking about shifting and scaling, location, or measures of location and measures of spread.
Mm-hmm.
Gotcha.
Yeah. And then sigma is.
Is it 5?
Standard deviation. So wasn't sometimes our mu, when it was, oh my gosh, I'm thinking on all of the words.
No worries, no worries.
Probably, is it this one?
I have it right under 5.2.
This is
Yeah.
5.2.
Yes,
5.2,
got it.
So
gotcha.
it's shifting.
Yeah, so when it comes to shifting and scaling, we
Like,
have,
ask questions on what you don't know.
yeah, I understand, yeah. So for the section 5.2, the things to watch out for are, there are measures of location. There are measures of spread. The ones for location are things like, say, the sample mean Y bar, or the median M, or it could be things like the min, quartile 1, quartile 3, or the max. And for measures of spread, that could be things like the standard deviation S, the interquartile range, or even the range itself, although that's a statistic that really doesn't come up too often, but we just talk about it here and there. So this would be measures of spread. And the takeaway with these things is that when it comes to measures of location, these things are affected by shifting and rescaling. And when it comes to measures of spread, these things are not affected by shifting the data. When we say shifting the data, we mean adding the same value to every single piece of data, but it is affected by rescaling. Rescaling means you're either multiplying or dividing every piece of data by the same value, and measures of spread are only affected by rescaling. So that's the breakdown of the two kinds of values there from section 5.2. And there will be an actual question from section 5.2 on the real exam. So if folks would like, we could go through a version of that problem. I'll leave it up to the class. Okay, let's give it a try. So yeah, this gets us started right here. You're thinking of maybe this one, problem 21?
Yeah, 21.
Gotcha. So let's throw this one in there. And let's see, I think we can fit it right there. There we go. So we've got kind of a cheat sheet right above to help us out. And this is an interesting one. It says, suppose the Idaho Falls police have set up surveillance on a residential street in a school zone that has a speed limit of 20 miles per hour. I live on a street like that, so this is a fun problem for me to make up. Over the course of the month, they collected a sample mean speed of 28 miles per hour, standard deviation 2.4 miles per hour, a maximum speed of 33 miles per hour, and interquartile range of speeds 3.2 miles per hour. So they collected a whole bunch of statistics. But if you ever gotten a speeding ticket, you probably know that sometimes you can't actually contest that. If you show up to court, you could just say something about maybe the radar's uncalibrated, or hope that the officer just was too busy to actually make it in that day. And so that's what's going on right here. Assume that it was discovered that the radar equipment was calibrated incorrectly. They really do have, it's sensitive scientific equipment. They really do have to pay attention and care for that stuff. Let's suppose it was calibrated incorrectly, causing all the data to be biased. So if that's the case, engineers could take the flawed radar gun, see how it was biased, and propose a function to, or an equation to correct all of the data values. Engineers have proposed the following formula to correct the data. So that's our next part. So the corrected value is going to be 1.2 times the old value plus 1.4, and this is in miles per hour. So it looks like the old radar gun was actually giving people speeds that were lower. People were actually going faster, in fact. And so maybe residents complained and said, hey, you should have caught that guy. Why are people getting let through? So we have a new formula to correct the old statistics based off a flawed radar system. And using that formula, we want to find the real mean, standard deviation, maximum, and interquartile range. So that's the setup so far. Here's where this kind of stuff gets foggy, though. It's okay to know what a measure of location is. I think that's not too bad. It does take some practice to memorize all the statistics for location. all the statistics for spread, a good way to think about this is think of these being as the two big statistics for spread, and essentially everything else is a location. The hard thing about this is knowing what part of your formula is shifting and what part of your formula is rescaling. So back to here, here's a 1.2 multiplying something. Is that a shifting or rescaling? Good call. So this part right here is rescaling. Let's see. Rescaling. Just put a quick arrow going this way. It's because it's multiplying is the major reason. You know what? That's a good thing to add to this review right here. Let's say rescaling means values are being multiplied. And rescaling means values are being added or perhaps subtracted.
I think you worded this better when we last talked about it, you said, when you're rescaling something, the distance between all the numbers stays the same, or changes when you're rescaling, but when you're just shifting it, the distance between all the numbers is equal.
Yeah, that's a great way to say that. Awesome. And that's why these things are unaffected. They measure spread, but spread doesn't change when you just simply shift the data. So that makes it this part right here.
The location's only adding.
Yes, measures a location. We do both the adding and subtracting and the rescale. And let me say that better. Affected by shifting and rescaling. Oh, my arrow is going the wrong way. Sorry about that. The arrow in blue should have been pointing this way towards shifting. Shifting means you're adding and subtracting different values. Rescaling means you're multiplying values or dividing values. Sorry, my arrow was pointing to the wrong thing there. That was really confusing.
And then I was like, oh, so, yeah.
So down below, we have shifting here for the 1.4. Yeah, that was a weird spot to kind of pause right there.
That was like, wait.
That was an F, I swear. So anyways, other questions so far? Okay, so let's give this a try. Starting with this one. Let's see, we have to find our statistics. The mean is 28 miles per hour. And you know, there's another thing that's going on in this problem. We also have to know that when it says the mean or the sample mean, it's referring to that one. So it's not necessarily going to give you the symbol. You have to know what the symbol is inferred from the words itself. So we have Y bar as 28 miles per hour. We're going to correct it. So here's the correction. Let me write it this way. Corrected is 1.2 times the old value, 28 miles per hour, plus 1.4. Here we use the full formula because measures of location are affected by both shifting and rescaling. The punchline to that is it just uses the entire formula. So back to the calculator for this one. 1.2 by 28 plus 1.4. So the mean speed was actually 35 miles per hour. Remember, this is a school zone at 20 miles per hour, so that's way more concerning than the old mean speed that was cited. Looks like on average, people are speeding like crazy down that street. So 35 miles per hour. Does that make sense to folks on that first go? Okay, let's change the focus then to next part. We have a standard deviation, 2.4 miles per hour. Standard deviation is a measure of spread, so this one we have to be extremely careful with. If we're dealing with a standard deviation, only affected by rescaling, and that means that part falls right off the formula. That's always really pretty weird. So when we go to calculate this, we'll say S. The old value was 2.4 miles per hour. Corrected is 1.2 times 2.4. So back here, 1.2 times 2.4 gives us a result of 2.88 miles per hour. Any questions so far with what we've got? Okay, let's try out the next one. Here's where it gets a little bit tougher. We have to scroll down. So we're going to rely on our memory for the next one, but we'll scroll up as necessary. So next is a maximum speed of 33 miles per hour.
So that's QR3, right?
QR3?
The maximum speed? Oh, no, it's max, it's not QR3.
Your quartile 3 is what you're referring to? Gotcha. The interquartile range would be involving the quartile 3, yeah.
And that,
Gotcha. So yeah, max is, in this problem, 33 miles per hour. But question for the class, do we use the whole formula or does a part of it come off?
We leave off the 1.4.
Kind
no,
of
we
depends.
leave on the,
You do?
oh, no, we should. Yeah, it's the full formula.
Seems like a little bit of debate. One question we could ask ourselves is the maximum a measure of position or is it a measure of spread? Exactly. So if it's a measure of position, that's the whole formula. Only measures of spread are the odd ones out. So watch out for S interquartile range. Probably don't worry as much about the range. I'm not going to ask that one, but it is true. It would be affected. Yeah. Yeah. Where were we looking at? Sorry.
Yeah.
Yeah, the white bar here is the sample mean. Yeah. Is that what you were asking about?
Yeah, I was just asking. If you have measures of location.
Oh,
and then how
gotcha.
it's-
Sorry, I didn't see that part of that question. It would be the same thing. Yeah. I think saying measures of, you know what? What is the best way to say that? We should go to the notes. Let's take a look at how the author states it.
It's the same concept as Y bar equal to X bar.
Let's see. Looks like the official way they say is position. So that should have been the way we should have indicated as well. And you know, that is actually pretty serious because this exam is hard enough as it is. Adding new vernacular to it doesn't make it easier. So thanks for mentioning that. We should say measures of position, just to be really sure. So that's the standard way we would say that there. And let's see, where else did we say position? Or location? Where was that? We kind of lose where it was.
I was looking at you did the shifting down there with that, I know it's shifting and scaling, but I don't know if that would be.
In the shifting and scaling notes where you have stuff written in and like reading like on how to,
Yeah,
In there, I think you have it.
on those sample 2 exam problems,
and over here.
online it has like how to do.
Oh yeah, there's answers at the very, very back here. Is that what you're referring to?
Yeah.
Gotcha. And
That's
gotcha. So over here,
the version where
the first one is yeah, that should have said a measure of position.
The third one's the set position. The third one's
Measure of location.
yeah.
Maximum is 11. Yeah, I see. That one should have said position. I'll make a quick note of that and correct the record on that one. Thanks for mentioning it. This was problem 21. I'll just put a quick note to say, be sure to say only measure of position, not location. Okay, thanks for spotting that one for me. I don't know why that was a hard one to find right there. Other questions at the moment? Okay, so let's go to about here next. And we've got our cheat sheet here as well. I think we're done with that note. And back to this one. Let's see, we're doing the maximum speed, 33 miles per hour. The thing we decide about this is maximum is a measure of position. And when we do a measure of position, it's the entire formula. So we can now say next that the max of 33 miles per hour corrected is the 1.2 times the old maximum speed, 33 miles per hour, add 1.4 miles per hour. And here's where we can use a pretty fun little shortcut on the calculator once again. We basically have done that before, right? So click up arrow to get to this one, hit enter. Now use the left arrow and just overwrite 33. Always a fast way to calculate if you can do the copy paste system like that. Now we've got 41 miles per hour. And looks like we're just about done. Last one is interquartile range. Any questions first? Okay, so our old value, IQR, was 3.2 miles per hour. And that corrected is, well, we have to decide what part of the formula we're going to use. Is it full formula or just a segment? Exactly. Anyone see which part we're eliminating? Exactly. Really pretty weird, but if they were talking about the interquartile range, it just says how spread out things are. And so moving the data 1.4 to the right has no effect whatsoever. So we'll just take 1.2 times the old IQR value. 1.2 times 3.2. For something like this, I would usually just type it right in. 1.2 times 3.2. And our value is 3.84 miles per hour. Well, we did, folks. I think this is a confusing question, so I'm glad we spent time on it. Sorry, say again?
Oh,
Oh, yeah, it looks like we ended on just IQR. Yeah. Yeah, absolutely. So for 5.3, any example in particular you want to take a look at? We have either body temperature or the post office. It looks like not too super exciting kind of stuff, but okay. So with this one right here, it says human body temperatures taken through the ear are typically a half a degree Fahrenheit higher than body temperatures taken orally. I had no idea about that. That's kind of interesting. Making this adjustment and using the 1992 Journal of the American Medical Association article that reports average oral body temperature as 98.2 degrees Fahrenheit, we will assume that the normal model with the average of 98.7, they added the 0.5 degrees to it. Find a standard, oh, let me start over. We'll assume that the normal model has an average of 98.7 degrees and a standard deviation of 0.7 degrees. No worries, Ashton. So, oh, hang on. And a standard deviation of 0.7 degrees is an appropriate body temperature taken through the ear. That was a hard sentence to read some reason. So essentially what they've said altogether is the mean we're actually going to use is that. Mu is 98.7 degrees Fahrenheit. And they gave us a standard deviation. This is one I would have no clue at. People cite 98.2 degrees all the time. That's just a corrected value. I don't think people talk about the standard deviation like at all. So unless I've just never been paying attention, but we've got a value now, 0.7 degrees. That's important because it's a reminder that the average is never the whole story. There is variation in humans and their body temperatures as well. There's just variation in everything in nature. Part A says, an ear temperature of 97 degrees may indicate hypothermia. Did not know that. Low body temperature, what percentage of people have eardrum temperatures that may indicate hypothermia? You know, that would be really, really important, right? Well, this one is from section 5.3. And so there's a couple ways to address this one. I'll leave it up to the class. Should we do this one with the calculator or using the 68 to 95, 99.7 rule? We'll say it's up to you since you asked the question. That's a good call. And that's really the purpose of that section, to kind of just visualize all this stuff. So that in 5.4, when we are using the calculator, things make a little bit more sense. There's the actual picture. So using that rule, here's how we'll start out. Huge, long horizontal bar going this way.
What was the name of that?
The 68, 95, 99.7 rule. It gives us the values of the area under this curve if you're a certain amount of standard deviations. This is 1 deviation away from the mean, 2, and then 3 deviations. So next, the curve goes about like this. Usually you want to draw it kind of big if you're using the 68, 95, 99.7 rule. The extra symbol here, n, is saying where you're dealing with a normal model. The mean on it is 98.7 degrees. And the standard deviation is 0.7 degrees. Horizontal axis is going to be temperature in Fahrenheit. I'll just use F for Fahrenheit. That's a difficult word to spell. I usually have to sound that one out. Next, the center is 98.7. And we want 3 tick marks going off to the right. They'd be in those relative locations. 3 tick marks going off to the left. And in the calculator, this is what we're doing next. Let's clear it out just so we have an empty space here. And doing this as efficient as possible would be something like this. So 98.7. And then for values to the right, add the 0.7. So plus 0.7. Hit enter. Double up arrow, enter again, and go times 2. We're just adding another 7 to get the next tick mark. So that's our next value. And double up arrow, hit enter, left arrow, and times 3. And that's their next value. So these are all values going to the right. 99.4, 100.8. Oh, thanks. I skipped one. 100.1, then 100.8. Thanks for spotting that. Next. Oh, gotcha. I guess there is a downside to doing it this way. You have a lot of visual information all of a sudden. Maybe it's better to go this way. Let's try this again. 98.7. Now for the lower bound, we go minus 0.7. And I'm going to change my strategy and just record the value. 98. Then back here, up arrow twice. Enter and hit times 2. Now we subtracted 0.7 twice. 97.3. Then double up arrow and make that a times 3. That's subtracting 0.7 3 times. Oh, sorry, question?
You said, add this, like the standard deviation and the average together to get that size right.
Exactly. So going to the right, we just added 0.7 to the 98.7. And then we did it again and again. And then, like you said, going to the left, same thing, except now we're subtracting each time. And this is subtracting it twice. And for a third time, we'd get the 96.6. Oh, there we go. 96.6. So those are all the temperatures. Next thing we would do to fill this out is start drawing some light borders. In these 2 regions that we've drawn out, there is 34% of the area in each of them. Then in the next area, starts to get a little bit foggy for me. Was this, anyone recall, 13.5? It's my guess. Awesome. 13.5%. This one was 2.35. Awesome. I never fully trust myself on these things. And how about for the far left? 0.15, I think. Sound accurate? Awesome. The nice thing about this is if you have all the values going to the left, then you don't have to worry too hard going to the right. Just copy them. So 13.5 here. 2.35 is here. And this tiny region, it's hard to point the arrow into, more than 3 standard deviations away, is 0.15. Well, these are percentages. I forgot to write it on some of them, but if you forgot your percent symbol, that's not a super major thing, I'd say. So now that we have the diagram on part A, we can answer the question. An ear temperature of 97 degrees may indicate hypothermia. What percent of people have an eardrum temperature that may indicate hypothermia? You know, I'm looking at this, and I'm starting to wonder if this was an actual question in section 5.3, normal models. Weird. I may have made a mistake on some of my values because usually if this is a real 5.3 question, the 97 degrees should have been right here. I'm a little curious how I did this one now. Let me take a look at the sample exam. So in chapter 5.3, part A, what percent of people have an eardrum temperature that indicates hypothermia? I'm not too sure if I answered that one. I just drew the model. That was really kind of weird. Sorry about that. I think I just had a mistake here in section 5.3, part A.
Yeah, I did put 98. It's supposed to be 98.7 in the middle, and you have 98.2.
Ah, so 98.2 here.
Well, that problem is,
Yeah, the question in the problem is correct, but the answer for me is 98.2, not 99.7.
Yeah, I think that might have been what's going on with this one. We will assume a normal model with an average of 98.7. Hang on. Average oral body temperature is 98.2. I used 98.2 on this problem. I still didn't answer the question though. That's still something I need to come back to on this one. So number 22, part A. Got to fix that one. Sorry about the confusion with that one out of nowhere.
Is that what you mean?
Well, let's see.
Yes, it says the average is 98.2, and then also average is
we will
98.7.
assume that a normal model.
Yeah.
Looks like it was just poorly written as a question. In all honesty, I think what was going on here was we have a normal of 98.2 degrees, but we have this information that's saying if you're taking it from the ear, it should be 0.5 degrees higher. And so that 98.2 turns into 98.7 is what my thought was on that.
98.7 is.
Yeah,
Yeah.
let me put that post-it note there just so I don't lose track of it. I'm confused too on this one. I feel like I did do this one incorrectly here. And I didn't even give us an answer. I just drew something. That's kind of strange. So
You probably got distracted.
yeah, it must have.
We're thinking-
Yeah, I'll come back to this one as well and correct the record on that. And just a standard thing to say at this point, if you see anything else that's weird on any one of these versions, let me know and I'll take a look at it right away. It doesn't take me too much time to fix them. And you're helping out everybody in the class, not just yourself. So back to the one we're doing here.
Yeah.
Yeah, I think this is the better answer. So when I go to correct the record on that problem, this is the value we ought to use. And the second struggle that we have is, now that we're using that value, this problem, well, this question right here doesn't line up with the 6/8 95 99.7 rule. I'll leave it up to the class though. We can either make a correction here and just say a temperature of 97 degrees may indicate hypothermia. What percent of people have ear temperatures below 97.3? So that lines it up with the problem right there.
So actually on my stats lab, the homework
Mhm.
website actually does that. It does give you percents that are not lined up like that.
Oh,
So they'll
weird.
ask you with 97 when our value is 91. Remember that?
Yeah.
Yeah.
Interesting.
It
It
does
really
exactly
should not. That's kind of strange. So if we did this as a My Stats Lab question, the best thing we can do is use that because it's the closest value. So how about we analyze it that way? Does that sound all right to folks?
We ended up, so doing the math on my stats lab on the calculator made the answer wrong. We had to use the chart that they gave us on the my stats lab.
Yeah.
Answer, but that's what we ended up.
I thought we used that number as a maximum. I went from there. Because I thought we used the actual math of the number they gave us, not the chart. Because the chart numbers didn't match.
I don't remember. I know some of them had to use the chart and not.
Yeah, there were some where we had to use both of them, there were some where they didn't match at all.
Well, I'll leave it up to the class again. How would you like to calculate it? The calculator or the diagram? Oh, I guess it's really was your question at the very beginning. We're using the diagram pretty much. So I guess we'll take this value, come up to the closest value right here. And if we're using the 6895.99.7 rule, the answer is going to be just take the 0.15 plus the 2.35, which would come out as 2.5% altogether. And just to compare, let's say using the TI 84. Let's see how close the answer is if we were to use this calculator next. In the TI 84, we'd hit second and bars to start off. And here's a good question for the class. If we're trying to find this area, is this normal CDF or is it inverse norm?
Find the area is, inverse.
Well, it turns out it would be normal CDF for that. Yeah.
Are we in fact like 3?
Yes. So for normal CDF, our lower value is going to be negative 10 power 99. So negative 10 power 99. Upper value would be 97.3 degrees. Value mu is 98.7. And then finally, value of sigma is 0.7. And this should be close to 2.5%, but definitely not exact. Let's see what we get. Well, that's as a decimal, so let's multiply by 100. So now, as an actual calculator computation, we were pretty accurate. It comes out as 2.27%, rounding up to 2.3. So this was a big overestimate. But again, sorry about that question there. Not too sure what happened with this problem, but it looks like maybe for some reason I just got the wrong value there. I think this is just a confusing question with multiple means being cited. But let's, yeah, so always give you a slightly different answer because this rule is just an approximation and the calculator is giving us a much, much more accurate answer. Well, on the exam, we're not directly asking a 5.3 question. It's going to be just a 5.41. So the 5.4 question, we couldn't use the 6895.99.7 rule. The numbers wouldn't line up even close on them. So your numbers are going to be something like here, like a 98 or 97.5, something like that. Other questions so far? Okay, well, just for the sake of finishing off this one, part B is saying what ear temperature values describe the 2.5% of population with the highest body temperature. And kind of a hint is, if we look at this, we got 2.5% before. So if we take these two, add them together, the result would be that there. So part B as a question did work out. Sorry, I'm not too sure again what happened to part A. But here we would say temperatures of 100.1 degrees Fahrenheit or higher. Those are the values that describe the 2.5% highest body temperature people, the people running the hottest, I guess you could say. Well, other questions, folks, with that one? Okay, thanks for asking about that one. Sorry for the disaster of what was going on with that question on part A there. Well, other questions folks would like to take a look at? That's a really good call. I think that'd be a great one to take a look at next.
And then if we have time afterwards, just bring that, can we look at the rule of thumb for the value
Yeah,
part again?
yeah.
So scatter plots, and what was the other one?
The rule
The rule of
of
thumb.
thumb, or the rule.
Or
Value
outliers.
are-
Yeah.
Gotcha.
There you go.
So I'm gonna just put a quick note here. Scatter, well, I guess I don't need that. We're doing that first. I'll just say next. 1.5 IQR. So that'll be my reminder to go back to that one. And for a scatter plot question, we should have a bunch of those up here. Let's see. So that's going to be in chapter 6. They start around here. I'd say the better scatter plot kind of problem would be one that asks you to do something with correlation, like calculate it. I think 29 would be a pretty good option. Does that look all right to folks for our scatter plot type question? Okay, let's grab this here. Okay, so it says, in the study of the tufted titmouse Parus bicolor, an ecologist captured 7 male birds. Oh, that's not a mouse at all. Parus bicolor. Let's take a look at that just to know what we're dealing with. So another bird problem, I guess. I'm not sure where all these bird problems are coming from. It must have been a textbook I grabbed problems out of. The author must have been a bird person. But that's what we're looking at right here. So that's the, might as well just put a screenshot in. So we've got a picture, there's our context. It says calculate the correlation coefficient R for these data. First, we should have a set of expectations. Do you expect R to be positive or negative based off what we see in the scatter plot? Exactly. So R is going to be bigger than 0, as like you said, there's a positive direction if we put a line to that data. Next thing we need to do to actually calculate the correlation is go back to the calculator, powered it on and hit the stat key to start. Hit enter. We've got to clear out this data. So let me clear here. Clear here. Now it's all wiped out. And here's the part where we're going to go really carefully data entering. Okay, so I think I've got all the data in. Anyone need any additional time? Yeah. Oh, thanks for spotting that. 83.5. Awesome. Good eye on that. I would never have spotted that since it was my mistake there. And notice, if I was doing this as a real exam question, I'm kind of doing it in a weird way. I really haven't read the context at all. I've just looked at a picture of a bird. You couldn't even do that on a real exam. But at least we're about to calculate the correlation coefficient. We're ready to do that. But for part B, I'm really going to have to read that problem and think about it in order to give a full response to that, because it is asking for the context. So let's keep on going in the calculator with all the data entered. Next step is to hit stat key once more. We move over to the calculate tab and down arrow until you get to option 8 called linear regression. This is the same thing we did in chapter 7, which is pretty helpful. We've practiced it a lot, but we only need one thing. So the thing that's difficult on this problem is you need to know that your answer is that, the thing on the very bottom. Let's add that to our notes just so that we can express that as well. Yeah, so it's in, just to see that again. Oh, it's not there. Let me try again. You go to stat. It's in the calculate tab, but even unwinding, imagine you were here, you just finished that off. You've entered the data. Right at that spot, hit the stat key, right tab, and then down to option 8. So let's add that to the screenshot as well. That is something that we do need. So your screen should look like this. Finally, hitting enter gives you this value, and this is what we're looking for. That thing there is the correlation coefficient. And let's see what we're rounding these values to. It didn't say. Well, if there's no indication on rounding, I believe we did say it on the real exam, but 4 decimal places is pretty standard for something like a probability or a correlation value. So 0.8033 will do the job. All you have to do in part A is just cite that value, 0.8033. Let me double check. Okay. What, any questions at all obtaining the correlation? Okay, getting the value of R is the easy thing. Now we have to think about the context. So let's read this again. In a study of the tufted titmouse Parus bicolor, an ecologist captured 7 male birds, measured their wing lengths and their characteristics, then marked and released them. So they captured 7 birds, kind of traumatized them to make some measurements, left them go off their merry way. It said next, during the ensuing winter, he repeatedly observed the marked birds as they foraged for insects and seeds on tree branches. He noted the branch diameter on each occasion and calculated from 50 observations the average branch diameter for each bird. The results are given in the table below, along with a scatter plot. So now if we go to a random row, that means this was one bird that the biologist captured, made some measurements, wing length 79.5 millimeters, and on average, this bird settled on branches at diameter 1.21 centimeters. It's kind of interesting. Looks like there is a correlation to how big the bird is, their wing length, versus where they actually target to settle on a branch. They're probably just doing that naturally, but it's kind of cool to see that there is a correlation there. And the correlation is high and positive. So now we have to interpret it using the context. Any volunteers for what we could say?
Very strong.
Strong relationship.
There is a strong linear relationship between, and what would we say next? Strong linear relationship between, what would come next? Any volunteers? Yeah, we pretty much just say these two values between the bird's wing length and the branch diameter they perch on. So hitting the context was really in several places where we said bird's wing length, we're mentioning context, branch diameter is mentioning context, and I said something about, let's see, well, we did say birds there, and we mentioned birds perching on stuff. So all that kind of stuff is context. There's a lot of ways to write a correct answer to this. It doesn't have to be exactly like this. I would say the major thing I'm looking for is the fact that we found a strong linear relationship. That's coming from the correlation. If it was like a 0.3, we'd say a weak linear relationship. If it was maybe a negative 0.7, we might have said a strong. You know what? I think we missed one thing here. There's a strong linear relationship, but is it positive or negative? Yeah, good call. We should say positive on this one. I totally missed that myself.
Like the right answer for English, it says there's a strong positive association.
Awesome. Yeah, association and relationship would be pretty interchangeable. I think positive was one thing we had to say. It goes in a positive direction with a positive coefficient. So let's see if we can bake that in here. There is.
When we're answering the essay, we have to, the exam, we have to use all 3, strong, linear, and positive.
Yeah. I would say actually the linear, if you dropped that off, it's kind of implied in this problem if you're being asked to calculate correlation. So I don't think I'd be as picky on linear, but the fact that it's a strong correlation and in the positive direction were the 2 things for sure to not forget. I forgot that one there, positive.
We did the one from, you did an example from the Mike Stats lab, and it said the slope was 0.06, which was the very weak one, and the line kind of went like this.
Yeah, that one was not even linear in the first place. That
Yeah,
was an
but
odd
that-
problem.
If that were to come up on the exam, would we put that as there's no relation, or there is a strong, not linear relationship?
I would say strong, not linear for that particular one. And I think I have something like that on these notes, actually. Let me take a look.
Yeah, and number 4, where it goes down and comes back up.
Yeah, on this one right here,
So that would be considered a strong relationship, which is not a linear relationship.
exactly, yeah. It's the one where we shouldn't even calculate a correlation on. And notice there's only 3 correlation values to this. That's on intention. That's how my stats lab should have gone. We should be giving, say, which one gets the 0.023 on this, would you say? Figure 3? Absolutely. This one looks like white noise, no real relationship. And it's 0.023 to kind of signify that. It's so close to 0, we're not really saying neither positive nor negative, really. Slight positive, but not by much. Then how about for this one, 0.892? Figure 1, absolutely. That one's not so hard to spot because it's going in a positive direction. It's a pretty strong one, so 0.892.
Got those line outliers though, they're not really outliers, they look like.
Yeah, these ones out here, yeah, that could influence it in a weird way as well, especially if they were lower as well. That could throw a lot of things off. It leaves this one as the odd one out, negative 0.975. And notice this is very close to being on a straight line. That's why the value is very close to a -1. This is the one that was the odd one out. Nothing really should be given for it. So sorry about that My Stats Lab problem where they forced us to put a value there. I think that really truly was inappropriate. This should have been, and this is if it's a real exam question, that's how it goes. No correlation.
So even though it's strong, there's no correlation.
Exactly. It's a very strong nonlinear relationship, but we can't measure correlation on it. Correlation only measures linearity.
Relationship can be strong, but not have a correlation.
Exactly. And I forgot to put this on the notes, so we'll just screenshot this whole thing. Bring it down here. And there was one last question about interquartile, the 1.5 IQR rule of thumb. Let me see if I can dig that one out. So let's see. This would be a data where that fits. Let's go only up to part B on this one, just for time consideration. This one's a bit of a race. Sorry about that. We're just out in our last few minutes. But for the IQR problem, here's how it would go. First thing we need to do is get ordinary summary statistics. So let's go to click the stat button, hit edit. I'm going to delete everything here just so that we can start off fresh. Next thing to do is import all the data. 128, 195, 188, 158, 227, 198, 163, 164, 359. So the reason we're doing that is we need some of the summary statistics, the 5-number summary. So with all that data imported, hit the stat button, go to calculate, and now we're doing one variable statistics. So hit enter there, enter a bunch of times. This is not the 5-number summary, but you just down arrow to get to the next set of statistics. And it's these values right here. So now that we have the 5-number summary, we really can't answer questions that way, but just for the interest of saving time, we'll throw a screenshot on this one.
What if my calculator says invalid DIM?
That might mean something about, I'm not too sure on that one.
Do that.
If-
No, I should go down.
So invalid dimension,
That's because we're not in the linear, we're not at the number 8, we're at the very first part.
Oh, yeah.
Oh, yeah.
We calculate this, and we're just using L1.
yeah, I read through that kind of fast, sorry about that. Okay, so next thing we do, IQ 1.5 IQR rule of thumb means you have to first calculate the IQR. And to do that, we take quartile 3 minus quartile 1. So let me hit clear here. Oh, second quit. There we go. Well, quartile 3 is 212.5 minus quartile 1, 160.5. And now we've got a value, 52 altogether. I should mention at this point, excuse me, we did run out of class time. And so if you have to get going, no worries. I totally understand. We're all busy people. So if you have an appointments, whether you're here in person or on Zoom, I totally understand. But just for the sake of, because this is an exam review and this will make it to the YouTube video, I'm going to keep going to finish off this problem right here. So let's keep on going. And if you have to get going, no worries. I totally understand. Next step of the process is we look on the lower end and we calculate this formula, quartile 1 minus 1.5 times the IQR. So for quartile 1, we're grabbing this value, 160.5, minus 1.5. For IQR, we just throw in that 52 we had. Now we're ready for a computation. Go 160.5 minus 1.5 multiplying the 52. Getting the number is not terrible. It's just a formula we throw things in. The tricky part is deciding next, are there outliers on the lower end based off this value here? I agree with you all. Folks are saying no, and that's because nothing is less than 82.5. If there was like a value of 60, then we would have said it's an outlier. So from here, we can say no outliers on the lower end. Next, we move on to the upper end. It's almost the same computation. We want to focus on just the changes. One change is you go to quartile 3, the upper quartile. The other change is you add instead of subtract. The rest of it is completely the same. So plus 1.5 IQR. Not too sure what happened to the highlighting there.
You slow down.
Oh, that is so weird. It's supposed to kind of stay put. Huh. Well, we'll fix that later on, maybe. Oh dear, I think I kind of messed up the whole thing. Might not be any bringing that back, so I'll just use an arrow to kind of resurrect that. It goes to there. Sorry about that. I think Microsoft's getting tired or something like that. For the next one, and let's just hope that stays in place this time, we take the upper quartile, 202.1.5 plus 1.5. Value for RQR again is 52. So we very nearly have it, folks. So 212.5 plus 1.5 times 52 gives us this output, 290.5. So now we make a comparison. Based on the data we have, do we have any outliers on the upper end? Absolutely. Which value would you say it is? Yep, so 359 exceeds our cutoff point on the upper end. So this tells us 359 is an outlier. Well, any questions, folks, on running through those steps? Yeah. Yeah, so the calculator, you hit the stat key to start, enter, and then just type in your data, just an L1 this time. Then the next step you take is you hit stat key, move over to calculate tab, And it's just gonna be option one variable stats for this one. So hit enter there and you're all set. Other questions so far? Okay, well, this will be a good stopping point for us then, folks. Thanks for sticking it through. And again, if you ever have to leave early, but the review went past the normal class time, it's always gonna be in the recording, so no worries if that ever happens. Totally understand.
Doesn't supposed to make a box, but that's on sure.
Yeah,